Okay, so what I have here, I drew part of a circle, and the center of the circle is over here somewhere. This is the top view of a car trying to navigate this curve. All right, now, in order for the car to navigate this curve, there has to be a friction force toward the center of the curve. All right, without that friction force, the car is just going to go off on a tangent path. So, if I want to look at a force diagram for this car, and now I'm kind of looking at the car from the side, not the top anymore. There's a gravitational force down. There's a normal force up. There's got to be a friction force toward the center of the curve. Now, because we're on a flat surface, and the car is not accelerating in the vertical direction, the size of the weight force and the size of the normal force are the same. Now, we know that the size of the friction force will be the coefficient of kinetic friction times the size of the normal force, and the normal force equals the weight in size, and the size of the weight force is mass times 9.8 newtons per kilogram. Now, since the friction force is the only force in the horizontal direction, it's the net force in the horizontal direction. It's also the net force toward the center of the curve, which equals the centripetal force, mv squared over r. All right, so I'm going to take this mu, and I should put a mu sub k there, because we're talking about kinetic friction. I'm going to take this mu k times m times g equal to mv squared over r, and I notice that the mass absolutely doesn't matter, it cancels out. So I'll solve this for mu k. All right, so that would tell you the coefficient of friction that's needed for a certain radius at a certain speed.